Welcome to lesson number 40, the last lesson of this course. So, we have come to the end of the journey and it is time to recollect the places that we had seen. So, in the last lesson we will take a quick review of the course, all the lessons that we have taken, and finally we will make some concluding comments. So, let us recall the objective and nature of the course as we had stated it in lesson number 1. So, the objective is to provide an exposure to the technologies that enable operation and control of modern industrial machines and systems. So, in short, I wanted it so that if you go and visit a factory which produces something, discrete manufacturing processes, steel plant, auto factory, you should be able to recognize much of the equipment and systems that you see, and also be able to make out how they work, right. So, that was the basic objective. So, as we stated in lesson number 1 that this is essentially a user's view. So, we for a large body of technologies which are used in for automation in various types of industries, we want to understand basically how they work and help in producing things, rather than contrasted to user's view is the designer's view. So, we do not want to this course is meant to be so in depth that you can start designing some of that equipment. That would be an order of magnitude enhancement of depth, and we have not attempted that here. We said that we will keep it application oriented. So, whenever we talk about a technology, we will try to make it always talk in the context of its use. So, how does that help? We will mainly talk about existing technologies, not very cutting edge technologies, but sometimes we will also try to capture the trends that are happening in industrial automation. And we said that this is going to be an interdisciplinary kind of course, in the sense that a lot of people, although this is predominantly electrical, in the sense that a lot of the depth or the exposure that is expected in the electrical discipline is more than in the other disciplines, but I guess still industrial automation technology is necessarily interdisciplinary and therefore of interdisciplinary interest. So, it will always be it should not be possible for somebody from mechanical or chemical to go through this course, maybe with a little bit of extra effort in building up the background in some of the electrical parts. So, that was the idea of the course, that to provide a view towards the breadth of automation technologies used in the variety of factories, and to try to understand the basic operational issues in that. That was in lesson 1. So, that was the major objective of the course. Then in lesson 1 we started the course in a very general note and try to define industrial automation. So, we try to motivate, we try to basically see how if we see that automation is, an industry is a systematic economic activity. So, and its primary objective is to make profit, then we try to find out how automation helps in making profit. And then we found that we introduced the concepts of economy of scale and scope, that and showed that in both respects automation helps. We looked at the various types of production systems, the various types of factories, batch processes, continuous processes, job shops, various kinds. And finally, we categorize the classes of automation system: fixed automation, flexible automation, integrated automation. So, and try to discuss that which kind of automation is actually good for what kind of factories. So, and then we in the next lesson we took a look at the architecture of industrial automation systems, and we introduced the automation pyramid and the levels of automation. So, we talked about the levels 0 of sensors and actuators, then level 1 of automatic control of various protections, alarms, then supervisory control, process monitoring, set point optimization, then production control, scheduling, maintenance management, inventory, then finally enterprise control, where we basically finance, business, HRD, marketing. And we said that all these for today's modern efficient factories, all these have to be integrated, and they must continuously exchange information from the field and decisions from the various parts in both ways, right. And this must be enabled by some sort of an industrial communication system. So, we also said at this point of time that in this course we are going to mainly concentrate on level 0 and 1, and we said that that is primarily industrial automation, and the higher layers are more in the realm of industrial information technology, and we are not going to cover that in this course. So, we started with level 0, and we first talked about the sensing system. So, we first took an abstract view of a measurement systems and found what are their typical structures, what are their typical static characteristics and dynamic characteristics by which you can describe the performance of any abstract instrument. We also looked at some typical sensor specifications of industrial sensors. Then, having done that, having taken a look at an abstract sensor, we started taking a look at the exact, the individual sensors for the typical process variables which are measured and which are controlled in an industrial environment like temperature. So, we talked about various kinds of temperature sensors and of course, their signal processing circuits. We talked about pressure, force and torque sensors. So, low pressure, high pressure, force measurement, strain gauges, torque measurement, and then we talked about position, velocity and acceleration sensing. Position, velocity and acceleration. Position and velocity sensing are very important for manufacturing, because from the point of view of manufacturing accuracies. So, we talked about position sensing. For example, speed control is actually a very important function. So, position and velocity sensing. So, we talked about position sensing, various techniques, resistive, inductive, capacitive, velocity sensing, various electromagnetic sensing, optical sensing techniques, as well as acceleration sensing. Then we took a look at flow measurement. Flow measurement is very one of the most widely measured and controlled variable in, especially in process industries, is flow, because as we have said that for temperature control you have to do flow control, for example steam flow control. For level control you obviously have to do flow control, because level is nothing but flow integrated. So, for pressure control you also have to do flow control because pressure is also in a way flow integrated, and then flow control is obviously flow control. So, the major variables, pressure, level, flow, temperature, all these in many cases come back to flow control, and flow control implies flow sensing. So, flow measurement is actually a very important component of process control. So, we talked about various the obstructive methods of measurement, including differential pressure flow meters like orifice and venturi, rotameters, turbine flow meters. We also talked about non-obstructive methods like electromagnetic flow meter, ultrasonic flow meters, cross correlation flow meters and things like that. After flow measurement, we took a look at signal conditioning, because signal conditioning today is electronics is giving us this feature that signal conditioning is very important, and there are some typical, for instrumentation there are some typical signal conditioners which are used with a large number of sensors. So, we talked about deflection bridges, both resistive, capacitive, then various types of amplifiers, voltage amplifiers, current amplifiers, voltage controlled current amplifiers, charge amplifiers. So, we took looks at various kind of amplifiers. Then filters are very important for removing noise. So, filters, active and passive filters. Then phase sensitive demodulators. I mean, in many cases the raw signal out of the sensor comes in a modulated fashion, for example LVDTs or strain gauge bridges. So, one needs to extract or demodulate the actual process variable that one is interested in. So, that requires a phase sensitive demodulator circuit. So, we introduced that. Then various other kinds of circuits like sample and hold, multipliers and multiplexers we talked about. Then we took a look at measurement noise and errors. Measurement noise and errors are so how does noise get coupled to a sensor? As we have seen, as we will see that noise is actually very important, because noise reduces measurement accuracy. It also creates problems when a sensor is giving feedback to a process control loop. So, if there is noise in the sensor, then as we have seen that the whole process control loop will start oscillating. Noise and errors can also give you other kinds of, for example, quality control problems. They can give you dimension errors. So, there we need to understand how noise gets coupled in circuits and some of the techniques and precautions to be taken. And then still we have to live with noise, and we have to characterize it. So, we have to know that the performance that we are getting out of our measurement systems, to what extent it is certain and to what extent it is uncertain. So, we need to characterize, we need to build a models of measurement errors, so that we can specify the quality of our products. So, we talked about measurement errors, and then we talked about that each individual, typically a system consists of subsystems. So, even measurement systems have various subsystems. So, there can be a primary sensor, there can be a secondary sensor, then a signal conditioner, then a signal processor. Now, each of them have their individual noise characteristics. So, these noises are generated and they get propagated through the system, and so we also discussed that if noise is propagated, how does it affect the final readings of the instrument. Finally, in today's automated environments, the sensors are typically connected to the data acquisition systems, which are connected to the computers, so that these process variables, which is the final reality in the field, and which is the real story about the production process, so that one can measure it, sense it, analyze it, monitor it, control it. So, all that is today done by computers. So, one of the first things is to get these process level signals into the computer, and that is done through data acquisition systems. So, we took a look at the architecture of data acquisition system, what they are made of and how they get the data into the computer. So, we started with sampling, then we talked about analog to digital conversion, and finally, we talked about the interface with the computer and the software which lets a human being or a computer program see the data, analyze the data for control purposes. This has completed. So, you see that we started with an abstract measurement system, then we took looks at some specific the major process variables of measurement, then we took a look at the typical signal processing circuits that are used for instrumentation and measurement, then we took at a look at the noises and the uncertainties and the measurement errors, and finally, we took a look at the data acquisition systems which gets the data into our computer. So, we have after that, now once the data is in the computer, we came to the second module of the course, which is on automatic control. So, we have first we have covered sensing, then we have come to automatic control, and in automatic control, the first in the beginning we talked about the basic purpose of control, and what are the typical performance issues like stability, like steady state errors, like transient what is the goal of a controller, and then we talked about the sources which create problems in control, like disturbance. So, having understood these general concepts, we first took up PID control, which is the still people say that even with so much advanced controls, about 80 to 90% of all industrial controllers are PID. So, it is important that PID controllers are looked at thoroughly. So, we talked about the basic PI and D modes, then the various parameters like process proportional band, integral time and derivative times, the effects of these changing these parameters on the transient performance of the plant and the steady state performance. There are some problems with D and I modes and how to circumvent them. Then we talked about PID controller tuning. So, these gains have to be properly set so that you have good response, and your because the response of the control loop is, as we have said, is directly related to a number of quantities, like like mainly product quality, the energy efficiency, raw materials that you are consuming and things like that. So, it is very important to have control loops well tuned, so that efficiency of production can be achieved. So, we looked at various methods of tuning, starting from direct computation, analytical computation based on models, then empirical tuning, which are based on experimental results, and and finally we took a look at auto tuning. So, auto tuning is that the controller itself examines the input output signal and then decides, and from there it decides the best controller parameters for this process, and then downloads it into the controller. Basically sets the PID controller parameters as those values. So, without human intervention, and we described the method using relay control systems. So, after PID controller tuning, we took a look at various different control structures which give great advantages in certain very common industrial situations in control. Like we started with feed forward and ratio control. Feed forward control is typically can give you very good performance in the face of disturbance, if disturbance is measurable. We also looked at ratio control, which is a kind of feed forward control. Then we took a look at typical techniques to control process time delays, which are very common because of material flow times, etc. in process systems, and also non minimum phase systems, where which are also some not uncommon, and for example in a drum level control. So, in such situations, some special control structures are actually required for effective control of the processes. So, we looked at these two particular kinds of processes, namely time delay systems and inverse response processes, and then found introduced some particular control structures which are used for controlling these. Then we looked at some special control structures which use multiple sensors, that is multiple measurements in a loop, or multiple actuation points. So, in particular, first we looked at cascade control and explained that how it can give you much improved performance than in non cascade control if some intermediate variables can be measured. Similarly, we took a look at selective control. Selective control is a control where you typically use for controlling spatially distributed equipment, something like boilers or furnaces. Similarly, multi actuator control, where there is only one variable being controlled, but that may be controlled using several actuators. So, typical case will be, let us say, HVAC control, that is heating, ventilation, air conditioning control, where the same room temperature is controlled, but when it is below ambient it is controlled using a different equipment or some kind of a chiller or air conditioning, while if it is to be maintained above ambient, then you use heaters. Similarly, we can use split range control. So, that this is split range control, and then we can use override control. Sometimes you operate a plant for let us say I mean from time to time your plant operational policy can change. So, sometimes you can operate for maximizing production, sometimes you can operate for minimizing some energy condition, some emergency condition, or from the point of view of safety. So, there can be various ways of controlling. So, I mean sometimes you can control using, there may be 2 valves and you can operate either one of them sometimes. So, in such a case, I mean when one control policy actually at times overrides the other and then drives a different actuator, but the same control variable is being controlled, in such case we have override control. So, in other words, we first looked at PID in depth, and then we looked at certain very special control structures which gives significant benefit. And finally, we took a look at some the factors which limit performance, typically the characteristics of sensors, the characteristics of actuators. All actuators have their rate limits as well as position limits. So, even if you I mean if you think a very large input can be given to a plant, it actually cannot given for actuator limitations, and it is for these reasons that the so called theoretical responses cannot be obtained. So, these constraints put a limit on the performance of the control loop. And similarly, we have limitations on sensors and we also have limitations on the process dynamics, or in other words degrees of freedom, that is things are related and we cannot all the time, it is not possible to have absolutely independent control. So, that is how much of independent control you can actually achieve depends on the degrees of freedom. So, these are some of the factors that actually limit control performance of industrial systems. Then we talked about the implementation, and in specifically we talked about how the PID algorithm can be implemented in various ways and how they are practically implemented in commercial industrial controllers. And finally, we talked about little bit about advanced process control, that is in fact we have not in this control module, we have not talked about some of the advanced process controls that are slowly being introduced. So, for example, we have not talked about model predictive control or nonlinear model predictive control, we have not talked about internal model controls or other kinds of control like state feedback controls. We have not talked about decoupling. So, there are several topics that we have not talked about, but still we talked about the major common control structures. Having talked in terms of the continuous controls, we shifted to logic controls, which are also equally important and equally prevalent in industrial manufacturing, which basically controls sequence of operations of machines and generate, they are often sometimes used for protection, sometimes used for supervisory control, where several sequences of control modes are executed. Sometimes they are used for generating alarms, they are more commonly used in discrete manufacturing. So, we first took a brief look at the theory of any control is actually based on models. So, we took a look at some discrete event system models, which and then tried to introduce and capture some of the industrial sequence control problems in terms of this discrete event systems model. Then we introduced the programmable logic controller, or the PLC. It is a class of equipment which sell in the market, which carry out most of the sequence control. And then we introduce the programming languages for this logic control, which are used in PLCs, in namely the relay ladder logic. Then we explain how PLCs work, how they get data, compute outputs, and then finally download into the field. We also introduced the RLL programming elements, that is the basic programming elements, and started discussing simple RLL programs. Then we talked about other RLL program features, various kinds of statements, arithmetic, data move and program control operations, and some other macro operations, which are basically a collection of a fixed collection of elementary operations. Finally, we introduced a systematic method by which these PLC controllers can be PLC programs can be written for some industrial control problems. So, we modeled the process as a state machine, and then based on that state machine we discussed how we can write a relay ladder logic program. In the last lesson we talked about the PLC hardware environment, the kinds of processors, the typical specifications of processor, memory, IO, the buses, bus extension, various kinds of special purpose IO modules like function modules, distributed IO modules, various kinds of communication and networking modules like industrial Ethernet. Then the devices that are used for programming PLCs, developing programs and then downloading, and finally man machine interfaces like which can be connected with PLCs. So, this completes our logic control module, and we come to one of the application areas, namely CNC machines, which are typically used for discrete manufacturing all over the world. So, we looked at the basic structural features and the basic operational features of CNC machines and how they are programmed, that is how the various cutting operations can be specified so that the machine can operate by itself. We also looked at the typical kinds of actuation requirements for these machines, and also took a look at the huge advantages that these machines can sometimes give you. In the next lesson we took a more detailed look at how the in a CNC machine there are basically you have to create, when you are doing manufacturing, you are actually removing metal by this shearing. So, relative motion between the job and the tool has to be created. So, for that the job has to move and the tool also has to move. So, typically what happens is that one of these motions is rotational and the other motion is translational. So, in any case there are precise position control, speed control requirements on these actuations or on these drives, so that the part dimensions are good and the part surface finishes are good. So, to understand how these motion commands are generated and how the motion control is actually carried out, this precision control in the CNC machines, in lesson 24 we looked at various kinds of command generation strategies like by interpolation. Then we took basically two kinds of control system called reference pulse and reference word systems, and how to generate them, and we actually took a look at one open loop reference pulse control and closed loop reference pulse and reference word control systems. So, after that we took a look at flow control valve. Flow control valves are very common and important elements in factories. So, we looked at 3 major kinds of valves: globe, ball and butterfly valves, and we took a look at the flow characteristics, their constructions, and how the valves are moved, and how the valves are moved precisely. For example, we took a look at valve positioners and what advantage these positioners give you. After flow control valves, we started taking a look at hydraulics and pneumatics. So, first we took a look at hydraulics, where we understood the basic principles, Pascal's law, then major hydraulic system components, and then we took a look at the components one by one. That is, we took a look at pumps and the motors, we took a look at the hydraulic valves both direction control valves as well as servo valves, and then we finally look at the final actuated control element or hydraulic cylinders. Then in the next lesson we actually continued this, and we took a look at flow and pressure control valves, and previously we mainly took a look at direction control valves. Now we took flow and pressure control valves, hydraulic cylinders, then 2 kinds of valves which are used very much in controls, that is in analog flow control. So, they are the proportional valve and the servo valve. So, and then finally we took a look at an electro-hydraulic actuation system. In lesson 28, we took a look at various typical industrial hydraulic circuits and saw how these techniques can be applied for industrial purposes. Then we came to pneumatics. Pneumatics is very similar to hydraulics, but there are slight differences. So, we took a look at system components again, compressors, pneumatic valves and their accessories, and finally we took a look at pneumatic logic, various kinds of reciprocating, and then various kinds of typical pneumatic circuits like reciprocating circuits with rapid retracts, reciprocating circuits with regeneration, so that the pressure energy is not wasted, and then various kinds of sequencing circuits. After that, we took a look at electric actuators, but before taking a look at electric actuators, we first understood that why it is a definite trend in among the industrial control or drives, that people are going for variable speed drives. Now, variable speed drives, what is the basic advantage of variable speed drives, and showing that variable speed drives can be huge, very significant energy savers. So, we first took a look at, we actually compared, fans and pumps are the predominant devices which are driven by motors. So, we found out that if the system load has a certain amount of variation, then having a variable frequency, although it is capital intensive, it is actually more expensive and more capital has to be invested, but this capital cost is actually coming down as the cost of power electronics is coming down, and on the other hand the cost of energy is going up. So, it now really makes a lot of sense to have variable speed drives, since they can save a lot of energy, and we saw basically from a pump or fan characteristic as to how a variable speed drive can make significant saving of energy to the extent of sometimes 50-60% or even 100%. Having convinced ourselves about the requirement for variable speed drives, we took a look at first DC motor drive, which is the most common, and so we understood the basic concept of operation of DC motors, and then we took two different kinds of DC motor drives. One is a line frequency AC-DC converter drive, that is rectifier, which is used for adjustable speed drives. Adjustable speed drives and servo drives are two different things. In adjustable speed drives, speed can be changed, but generally the drive is operated for significant amounts of time at a particular speed reference. while in servo drives the speed continuously keeps changing. So, the kinds of power electronic drives that you use for adjustable speed drives and servo drives are different. So, we took a look at two different kinds of drives, one with a converter, one with an rectifier AC-DC converter and another with a DC-DC converter. So, we went on, this is a continuation, lesson number 33 of these switch mode DC-DC converters, and then we also since these are used for BLDC drives, we also took a look at brushless DC drives, which are essentially SC motors. Then we took a look at induction motor drives, and in the case of induction motors we mainly concentrated towards the adjustable speed drive, because induction motors are generally not used for servo drives, although they can be, but they are much less used for servo drives. Generally DC and nowadays more BLDC drives are being used. So, then we took a look at two kinds of motor drives. One are stepper motors, which are used for which are very simple and cheap drive electronics, and are used for non-critical applications and for smaller applications having smaller power ratings. And then we also took a more detailed look at BLDC drives, which are becoming very popular, basically because of the magnet improvements in magnet technology. Then we so this completes actuation, and then it turns out that electronics is making very significant inroads into all areas of technology and also into industrial automation. So, now what is happening is that most of the industrial automation devices like sensors, actuators, valves, they are having electronics on the field or electronics embedded in them. So, they are all becoming microprocessor controlled devices which give previously huge capability to these mechanical or electromechanical devices. So, now you can have a flow control valve which has electronics on it, which can do all sorts of signal processing, auto calibration. It can send values, it can monitor its own failures, it can calibrate itself, it can even connect on a network. So, all this is possible because every device is having computing and electronics technology embedded in them. So, we thought that it's a good thing to take a look at the basic embedded system technology, because it is becoming so common and all pervasive in all aspects of our life and also industrial automation. So, we took a look at embedded systems and understood its basic types of hardware components and basic software characteristics, the kind of software that are used in that. Then we took a look at many of these systems are actually operate. For example, a CNC machine. A CNC machine has various, at least 3-4 processors. It has access controllers, it has PLCs, it may also have front end processors which manage the man machine interface. So, all these multiprocessor complex systems generally work under some sort of a real time operating system. So, we took a look at real time operating systems and their features, and one of the essences of real time operating systems is that there are several time critical tasks which are in parallel executed in the system. So, how to schedule them, which one will be computed after what, whether they can be interrupted in the middle or not, under what conditions. So, these are one of the major aspects of real time computing, which is a feature of embedded systems used for industrial automation. So, we took a look at this real time task scheduling, the basic principles of it. Now, once you have these embedded devices with this embedded electronics and embedded processors in them, then the whole new world of opportunities open up. So, now since you have processors on each of these devices should be able to communicate with each other, and there is very significant benefit that can arise out of this communication. I mean, a much more significant coordination would be possible, and optimization would be possible. Lot of data can be acquired, knowledge can be gained, operations can be always kept in a very tuned manner by continuous adaptation. So, all sorts of documentation can be made. So, all sorts of benefits can accrue if these intelligent automation devices can be made to communicate. So, it is from this concept that now people are saying that these devices all should be on a network. So, and one of the very emerging and very prominent network standards for the industrial automation market is the field bus. So, in this lesson and the next, in lesson number 37, the field bus protocol, network protocol was looked at. So, it, like all network protocols, this is also organized in terms of various kinds of layers. I mean, in a network, data is the whole data basically gets transformed. You are at the top level, you are generating information, and when you are sending it down, finally it is becoming ones and zeros, and it is at the destination, those ones and zeros are being received and they are being processed in various ways, so that finally you get back the information. So, this is actually carried out through layers of softwares. So, we have first talked about, so we started discussing, and in this lesson we talked about the physical and the data link layers, the various features and the network protocol architectures, and also the mechanism of arbeiting communication rights. One of the problems of having a bus is that the bus is electrically shared, and therefore people cannot, I mean, the devices, only one device can talk at a time. So, there is a need to understand who is going to talk when. So, there are elaborate rules have to be formulated for that. Otherwise, when somebody is talking or some device is transmitting data on the network, if another device starts transmitting some different data on the same network, then the data can get corrupted. So, we took a look at some of these models of arbeiting communication rights on the buses, and taking a look at how that actually turns out for cyclic and acyclic communication. Once the basic, so this will ensure that the basic data packets at the low level, they can get transmitted reliably from one point to the other, and then you have to talk about the application and the user layers. So, how that is, when one device looks at another device, how it comes to know that what is how that device is made of, what is it doing, the interpretation of the variables that one device is sending to the other. So, all these issues are dealt with at the application and the user layers, and we mainly discuss the function blocks, which is the abstract model for any field bus device, and we also discuss the issue of obtaining synchronization throughout the network. So, doing network management and doing time management over the network. This more or less completes, so if you go back, you have seen that we have discussed sensors, that was in the first module. Then we have discussed controls, both analog controls as well as sequence controls, and then we discussed various types of actuators. So, we discussed flow control valves, we discussed hydraulics, we discussed pneumatics, and we discussed electrics, that is basically motor drives, and we also discussed that how these can save a lot of power. So, then finally we discussed the electronics, which makes them intelligent and makes them and enables communication among them. So, once you have all these devices, these level 1 and level 0 devices on the network, so all their data are available, then it would be possible to do system wide coordination and system wide optimization. And in fact, it is precisely this which is done at the automations are at level 2 and level 3. In absence of this electronics and communication, typically these optimizations and these coordinations are done at a much slower scale, basically by the operator. So, the operators just take looks at those values and then they operate the process. But once these data are available on the computers over the network, then there are possibilities of doing much faster and much more pervasive coordination among in the factory. So, actually that is what is to be done, that is what is done in the case of in level 2 and level 3 automations. So, in the last in the penultimate lesson in brief, we actually talked about the higher layers. As we said that we are not going to discuss the higher layers in great depth, because of various reasons. Because firstly, it takes time to cover only level 0 and level 1. So, we do not have enough time. Secondly, higher layers are often very domain dependent, while level 0 and level 1 technologies are domain independent and they apply to a wide variety of plants. If you want to know how to do set point optimization, then you have to only talk about set point optimization for either a distillation column or a boiler or whatever. So, they become very process specific and therefore difficult to discuss in a course. So, in this lesson, in the last penultimate lesson, the basic features of supervisory control and manufacturing management were discussed. So, we talked about level 2 automation functions such that set point optimization and process monitoring. So, one they actually this is a wrong, it should be set point generation and process monitoring. This is a typo. Then we talked about level 3 automation functions, where we talked about basically planning, scheduling, and basically planning and scheduling. So, how the various we did not go into much depth though. Then on top of that we have, so we have level 2 systems and level 2 systems which are still with the controls. Then some bit of level 2 and basically level 3 systems are generally reside in a different type of computer, and their computing and techniques are completely different. So, they are called manufacturing execution systems. And then in level 4 we have business systems which employ technologies like supply chain management, enterprise resource planning, and therefore and basically they generate long range plans, they generate market projections, they actually decide how much order has to be taken, what are the commitments, deadlines, and then they pass it on to the manufacturing execution systems, which in turn then decide that with the available equipment, manpower, raw materials, how exactly production should go. So, it's such that all the production deadlines are met, and then these production sequences and detailed production sequences are passed on to the supervisory controller, which then actually gets about producing. So, this is the way it goes on. So, in the last lesson we discussed these higher level automation functions. So, that brings us to the end of this lesson, and so having discussed what has been covered, we should also take a look at what has not been covered. At least we should be aware of some of the things that we have not covered, which were also relevant. So, for example, as we have said that we have mainly concentrated on level 0 and 1. So, level 2 and 3 have not been covered in great detail, that is the first thing. But even in level 0 and 1, there are certain parts which could have been covered, but could not be covered. You have to always leave out certain things. For example, we did not take a detailed look at metrology, or which are widely used for quality control. We did not take a look at analytical instruments which are used for process product composition testing. We did not look in great depth on instrument standards and calibration. Similarly, in terms of control, as we said that while we looked at the PID controller and some of the standard process control architectures, there are some advanced controls which are coming and which are gradually becoming gradually also being applied in processes and manufacturing. We did not discuss them, like nonlinear model predictive control. The PLC treatment was also kept more or less, the standard techniques. Like PLCs have several programming languages, so we did not discuss all of them. We only discussed the relay ladder logic in detail, and then the sequential function chart in some detail. So, in other words, what I am trying to say is that in case somebody is interested, one can go ahead and read other supplementary or advanced level material for knowing the latest in these fields, which would be the beyond what has been covered in this course. Similarly, in level 2 we did not discuss various kinds of quantitative optimization techniques, linear, nonlinear programming. We did not discuss advanced monitoring and diagnostics techniques, some of which have just started becoming being applied. They are quite advanced. We did not deal with, as I said, level 3 and 4 we hardly talked about it, and there are very detailed scheduling and optimization techniques available. For example, enterprise resource planning can be a course in itself. So, having said that, I would make the final concluding comments of this course. This course was thought of because such a course actually is rare. You don't have books or materials which discuss these, the industrial automation technologies all within one covered. So, that was one of the main motivating factors of having this course, and this course it was also felt that can be useful for various kinds of student backgrounds for students from engineering undergraduate students, from mechanical, chemical, electrical, etc. So, the major focus and coverage was kept suitable for the major focus and coverage was kept suitable for the undergraduate levels. We have just discussed what has been covered. Reference and supplementary materials have been used from a variety of sources, several texts, internet, my own class notes, handbooks. So, because it's simply because in fact they were, but in all case, we have not, within the limits of this course, it has not been possible to, it wouldn't have been possible to cite all of them. So, we have left them out altogether, but in all cases, while I have certainly referred to various kinds of material, I have tried to present them in my own ways. So, that way the presentations in many cases, in all cases are original. We have not been able to give, again because of we have not been able to discuss numerical problems. So, in fact, one has to find out numerical problems from individual modules, like for example, numerical problems on control can be found from process control books. Similarly, drives maybe from power electronics and drives books and things like that. Another thing is that under the same NPTEL program, an associated web based course has also been developed by myself and Professor S. Sen of IIT Kharagpur, and we will be able to give some of these refer to address some of these problems of numerical problems, questions, answers, references in those web courses. So, that is all for today. I hope this course would be useful, and well, yes, after recording these courses, I am right now teaching these courses in my own classes using the same set of slides, and I have discovered a few errors. So, while in the final version some of these errors will get removed, I am sure that some of them might still stay various kinds of errors. I hope there are no major errors. So, in case there are errors and if you declare, if you find them and you can inform me, I will be grateful, but I will apologize in advance for any errors that may be present here. But I always feel that, you know, if one can correct an error in a particular part of any learning material, he probably learns that part of the material the best. So, there you are. This is the end of the course. Thank you very much and bye bye.
(1951). A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the NR Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today, IIT Kharagpur